Welcome back, learner. Usually when we approach a seemingly impossible problem, we look for a sharper tool
Yeah.
or, maybe a better angle of attack within the same rule book.
Right. Yeah, you try to push harder with the tools you have.
Exactly. But what if the rule book itself is the trap? Today we're taking you into the heart of a puzzle that is so notoriously unsolvable that veteran mathematicians literally pull young grad students aside to warn them off.
Oh, yeah. They call it a career ender, which, I mean, for a math problem is pretty wild.
It really is.
That.
We are talking about the Collatz conjecture, or you might know it as the Syracuse problem, or the Hailstone sequence.
It is basically the defining mathematical trap of the modern era. It's a problem that is deceptively, almost childishly simple to understand, but it's completely impenetrable using standard number theory.
So the reason we are doing a deep dive into this today isn't just to rehash a failure. We're looking at this groundbreaking, completely mind-bending paper by Enkamgalan Nosen Jargal.
Yeah, the geometry of convergence.
Right? The geometry of convergence. Solving the 3n+1 dynamical system via infinite fractal descent. And our mission here is to explore how this paper claims to finally crack this impossible problem.
And spoiler alert, it doesn't do it by just being, better at arithmetic.
No, it completely flips the script. It treats numbers not as these abstract concepts on a chalkboard, but as physical, geometric objects that exist inside a four-dimensional space.
And that shift in perspective is, well, it's everything. For you listening, this is really a profound masterclass in lateral thinking. Because when the rigid rules of your discipline fail you, sometimes you don't need to push harder.
You just need a new discipline.
Exactly. You need to pull the problem out of its native environment entirely. You map it onto this alien landscape where a solution actually has the physical space to exist.
Okay, let's unpack this. Just to make sure we are all starting with the same baseline, let's outline the trap itself. The Collatz conjecture is built on two simple rules, right? Applying to positive whole numbers.
Right, just two rules.
If you have an even number, you divide it by 2. If you have an odd number, you multiply it by 3 and add 1. And you just keep applying those rules to whatever number pops out.
So if you start with 5.
Right, 5 is odd. So you multiply by 3, you get 15, add 1, getting 16.
Yeah.
16 is even, so you have it to 8, then 4, then 2, then 1. And, well, 1 is odd, so 3 times 1 plus 1 brings you right back to 4.
And there it is. You end up trapped in that 4-2-1 loop.
Right. So the conjecture asserts that no matter what positive integer you start with, whether it's, 7 or 7 billion, or a number so large it exceeds the count of atoms in the observable universe, it will inevitably crash down into that exact same 4-2-1 loop.
It always falls, like a hailstone, hence the name, the hailstone sequence.
Yeah. But the wild part is, no one has been able to prove why. I mean, if I start with a massive, unwieldy number, why doesn't the sequence just occasionally catch a thermal draft and spiral off into infinity? Why does every single trajectory terminate at the exact same ground state?
Well, the paper points to what Nosen Jargal identifies as a methodological gap in present-day mathematics. He draws on the work of mathematician Geoffrey Ligarius for this.
Okay, and what did Ligarius figure out?
Ligarius observed that this problem sits way too high in the arithmetical hierarchy. It touches on generalizations that are mathematically undecidable. Pure arithmetic just fails completely here, and it's all because of that innocent little +1 in the odd rule.
Wait, let me make sure I'm wrapping my head around that. Multiplying by 3 isn't the issue, it's the addition?
Precisely. Because multiplication preserves the structural lineage of a number. Its prime factors remain, orderly. But when you add 1, what the paper terms additive innovation, you completely obliterate that multiplicative structure.
Oh, wow.
Yeah, it's like shattering a crystal and trying to calculate where all the microscopic shards land, only to have to rebuild a completely different crystal on the next step.
That sounds exhausting.
It is. Standard number theory relies on structural predictability. And the 3n+1 rule is basically designed to be a structurally unpredictable wrecking ball.
Which means we are trying to map a chaotic system using a ruler that breaks every time we take a measurement.
Exactly.
So if pure math is fundamentally ill-equipped for this, Nosen Jargal doesn't just invent new math. He moves the integers into a completely different dimension.
Right, he introduces a radical framework called infinite fractal descent, or IFD.
So we stop treating integers as one-dimensional scalars, like just simple quantities on a number line. And instead, we treat them as localized patterns of informational density inside a four-dimensional topological manifold.
I know that sounds dense, But to really grasp the mechanics of what Nasanjargal is doing, we have to visualize that geometry. By pulling the problem out of one-dimensional arithmetic and placing it into a four-dimensional space, we aren't balancing equations anymore.
We're doing physics.
Exactly. We are tracking a physical object moving through a physical space that's governed by entropy, mass, and fluid dynamics.
So if you're listening and trying to picture a four-dimensional topological manifold, don't overthink the fourth dimension right now. Think about trying to solve a massive 2D maze on a flat piece of paper.
Okay, I like this analogy.
The walls are fixed, right? And you
Okay.
keep hitting dead ends. What this paper does is equivalent to picking up that flat piece of paper and folding it into a 3D origami shape. Suddenly, in this new physical geometry, the start of the maze and the finish line are literally physically touching.
That's a great way to put it.
But because we are treating numbers as physical objects now, we have to understand the specific physics of the universe they live in. And the paper calls this the computed universe.
Right, and this computer universe is built with very specific parameters. It's modeled as a logically complete entity, specifically a 3 torus.
Okay, let's ground that concept for a second. A 3 torus is essentially a repeating space. If you think of a classic arcade game like Asteroids, where your ship flies off the right side of the screen and instantly appears on the left side.
Right, or flies out the top and comes up through the bottom.
Exactly, that's a 2D torus. So a 3 torus is that same concept, but in a three-dimensional room. You walk through the ceiling, your feet land on the floor.
Taking that a step further, the fourth dimension here is time. But time in this computed universe isn't like a continuous flowing river. It moves in discrete, rigid frames called the universal tick.
Which the paper synchronizes conceptually to Planck time, right?
Well, yes,
Yeah.
the absolute smallest measurable unit of change. So with every single universal tick, the system updates its state to minimize local informational imbalance. It's an environment that's perpetually seeking structural equilibrium.
So the number we are calculating in the collapse sequence isn't just a value anymore. It actually has physical weight in this space. Its size represents its recursive depth, basically, how much computational energy it costs to sustain that number's existence inside this 3 torus.
Yeah, it requires energy to exist.
And those simple collapse rules act as the physical terrain. They form an informational landscape. When you hit the odd rule, the 3n plus 1, you are hitting a ramp. You are moving the sequence up in energy. When you hit the even rule, divide by 2, you are hitting a cliff, dropping the energy down.
And Nasanjargal defines the mechanisms interacting with this terrain as operators. So the odd rule operates as the kinematic packing factor.
I actually found a great way to visualize this while reading the paper. Imagine the number is a little wind-up toy car.
Oh, I love that.
The kinematic packing factor is the act of turning that key and winding it up incredibly tight. You are injecting what the paper calls informational tension and vorticity into the system. You are cramming potential energy into this localized spot inside the manifold.
That physical translation is so vital because that tension requires geometric space, and the even rule, the division by 2, that functions as the dissipation operator.
So that's when you let go of the car.
Exactly. That is when the wheels of your toy car spin, bleeding off all that stored tension into the surrounding manifold. The paper actually models this geometric energy decay exactly like viscous friction in a fluid.
Which brings us to a piece of structural genius in the math that Nasanjargal highlights. He renames the 3m plus 1 rule the forced parity operator.
Yes, this part is brilliant.
Because, think about the arithmetic for a second.
Yeah.
If you take an odd number, multiply it by 3, it stays odd, always. But when you add 1, you guarantee it becomes even.
Every single time.
5 times 3 is 15, plus 1 is 16. 7 times 3 is 21, plus 1 is 22. It happens 100% of the time.
What's fascinating here is how that mathematical certainty translates directly to physical geometry. It means that every single time you apply the kinematic packing factor,
Every time you wind up the toy car.
right, every time you inject tension, you are geometrically forced to hit a cliff on the very next universal tick. The system physically prevents you from stringing together multiple packing operations.
Wow.
It's an inherent braking mechanism. You pack energy in, and the manifold demands you immediately dissipate some of it.
Okay, but here's where it gets really interesting. And let me push back on this a bit. Because if you have a brake, but the engine is still more powerful, the car still speeds up.
That's true.
In the sequence, multiplying by 3 is much stronger than dividing by 2. You wind the car up 3 turns and let it spin off 1 turn. It's still netting positive tension. So, isn't it true that the trajectory could still theoretically achieve escape velocity and shoot off to infinity? I mean, if the universe is infinitely large, it could hold infinite tension.
Well, you're touching on the exact reason arithmetic fails. But Nassau doesn't assume the universe is infinite. The computed universe has an absolute structural limit. It's called the fractal density constant.
Right, density constant.
Yeah. This manifold simply cannot contain infinite localized tension. It physically runs out of room.
Wait, isn't that just a massive cheat code?
How do you mean?
If you can't solve an equation to prove it doesn't go to infinity, you just invent a custom universe with a built-in ceiling and say, look, it can't go higher than the ceiling. That sounds like fitting the universe to the answer you want.
I can entirely see why it looks like a convenient trick, but we have to examine how that ceiling is constructed. Nassau isn't just arbitrarily drawing a line in the sand.
Okay, so where does the ceiling come from?
The fractal density constant emerges directly from the translation of the integers themselves. The topological manifold is built from the properties of the numbers, meaning the structural ceiling is a mathematically necessary feature of the space. It's not an artificial lid. It's governed by something called the unified bounding inequality.
Okay. Let me try to map that out for the listener, because there is a bounded divergence phase transition graph in the paper that makes this really clear.
That graph is key, yeah.
Picture two lines on a graph. The first line represents our toy car getting wound up, right? The packing factor. It is desperately trying to curve upwards exponentially, building toward infinity.
Trying to run away.
Exactly. But above it is a second line, the structural ceiling of the space itself. And that ceiling doesn't grow exponentially. It flattens out logarithmically. It curves over the system like a heavy dome.
And the unified bounding inequality dictates that as the informational mass of the number grows, it becomes tightly bound by the geometry of the space. The ratio of the packing energy to the dissipation energy is physically required to stay beneath that logarithmic dome.
So, as the number tries to push higher, the ceiling literally squeezes it. It starts running out of computational volume in the 3 torus. And what happens when a trajectory gets squeezed against that ceiling?
Well, the geometry forces its hand. As the tension approaches that spectral limit, the probability of the sequence encountering a number that is a pure power of 2 approaches 100%.
Pure powers of 2. You mean numbers like 1664 or 1024?
Exactly.
Why are they so important here?
Because in this 4D manifold, a power of 2 is the most stable resonant pattern that can exist. It acts as a zero-friction dissipation well.
Wait, a dissipation well? Like a sinkhole?
Yeah, exactly like a sinkhole in our terrain, because a power of 2 can be divided by 2 repeatedly, all the way down to 1, without ever hitting another odd number. It means there are no more ramps.
Just one giant continuous cliff.
Precisely.
So the sequence gets wedged against the ceiling, the pressure builds, and the universe essentially forces the trajectory into one of these sinkholes to relieve the pressure. The paper describes this breach as a terminal cascade. The system entirely breaks down.
It's a nonlinear collapse. Once it hits that dissipation well, it's purely viscous decay. The magnitude halves and halves and halves rapidly until it reaches the 4-2-1 loop.
Which IFD identifies as the absolute minimum energy ground state of this universe.
That's the baseline. It can't drop any lower.
To really lock in how this cascade works, the paper references the dissipation matrix and draws a brilliant isomorphism to the abelian sandpile model.
Oh, the sandpile model is such a good visual for this.
It really is. If you aren't familiar with it, imagine dropping grains of sand, one by one, onto a flat table. At first, nothing much happens. A small pile forms. You keep adding grains, and the pile grows higher and wider, absorbing the new sand without an issue. The tension in the pile is increasing, but the structure remains stable.
The pile is building potential energy. It's moving toward a critical slope.
Exactly. And eventually, the pile reaches an angle of repose where it physically cannot get any steeper. It hits its structural ceiling. And when it does, adding just one single grain of sand, which is our 3n+1 step, causes the entire side of the pile to give way in a massive avalanche.
And that avalanche is the terminal cascade.
Right. All that accumulated mass redistributes instantly until the pile flattens out into a stable state again.
If we connect this to the bigger picture, the sandpile model is the absolute hallmark of self-organized criticality, or SOC. What the paper proves is that the collat sequence naturally and inevitably drives itself toward the edge of chaos. It evolves to a critical state where a single update step will trigger an absolute avalanche of dissipation. And Nassau actually maps this using principles from fluid dynamics.
I have to admit, mapping a number puzzle to fluid dynamics feels like a massive leap. How does water flowing relate to multiplying by 3?
It's through the concept of a turbulent energy cascade. When you have a rapidly flowing fluid, you generate massive, large-scale eddies, swirling vortexes of high energy. But in fluid dynamics, those massive eddies are inherently unstable. They fragment, they break down step by step into smaller and smaller eddies, transferring their energy downward.
So the giant unwieldy integer in our sequence is the massive eddy. And
Yes.
every division by 2 is that eddy breaking into smaller swirling currents.
Yeah, exactly. And eventually those currents become so microscopically small that the kinetic energy is completely dissipated as heat by the viscous friction of the fluid itself.
That's incredible.
In turbulence, this breakdown obeys the Kolmogorov scale, which mathematically predicts how energy transfers from large scales to microscopic dissipation. Nazan-Jargal proves that the informational energy in the Collat sequence obeys this exact same structural decay.
So the rate at which the mathematical tension dissipates perfectly mirrors how physical turbulence resolves itself.
It's a one-to-one match.
So what does this all mean? Let's take a step back and look at the absolute paradigm shift we just walked through. For almost a century, brilliant minds were stuck in that shifting 2D maze, trying to use pure arithmetic to prove why a simple string of numbers wouldn't just grow forever.
And getting nowhere.
Right. But by completely abandoning number theory and viewing the problem as an informational fluid moving through a rigid four-dimensional space, Nazan-Jargal proved that infinite divergence is geometrically impossible.
The space won't allow it.
You can wind the toy car up as much as you want, you can pile the sand as high as you dare, but eventually the geometry of the space intervenes. Every trajectory must hit that logarithmic ceiling, fall into a power of 2, and collapse in a massive avalanche right back to the stable 4-2-1 baseline.
This really raises an important question for you listening right now. When you look at your own learning process or the seemingly intractable problems in your own work, are you banging your head against a wall using tools that are fundamentally unequipped for the job?
That's a great point.
Because the arithmetic hierarchy couldn't solve the Collat's conjecture because it lacked the dimensions to capture the reality of the sequence. The real breakthrough might require stepping out of your native field, entirely taking your problem and mapping it onto physics or biology or economics to finally see the geometric boundaries that actually govern it.
I want to leave you with one final, slightly mind-bending concept to mull over before we go. The success of this infinite fractal descent model relies on the fact that discrete recursive algorithms inherently limit themselves when placed in a spatial framework. Right. The paper notes that fundamental constants in our physical world, like, say, the rate acoustic energy decays in a room, or how astrophysical masses scale in space, they appear to emerge purely as harmonic ratios required to keep space-time coherent. They are structural necessities.
Yeah, they have to be there.
So, if a mathematical algorithm behaves exactly like a physical fluid, and physical reality regulates itself like a self-correcting algorithm, could it be that the abstract code we write on our computers, the math we invent in our heads, is actually invisibly bound by the hidden geometric physical laws of the universe itself?
It really suggests that the math we think we are inventing is merely mapping the physical constraints that were already holding the universe together.
It definitely makes you look at a simple math equation differently. So keep questioning the reality around you, learner. And remember, the next time you feel stuck in a maze, well, maybe you just need to fold the paper.